hot take, the periodic table is actually cool. There's 118 elements. Which ones are S tier? And what are the surprising underrated elements that are further down the list that might not be S tier but are actually really important?
2 hours later.
Oh my God. We did it, people. We freaking tier listed. We did the whole tier list. Let's get a good look at our tier list. Yeah, these S tier elements, hydrogen S+, carbon for everything, making all the chains, making all the structures in life, so amazing. Silicon, the sand of Earth, and also the future substrate for intelligence. And then so yeah, today we're going to look at all those elements, all 118 of them, and ranking them. And we're going to do 1 through 30 first. And actually for 31 through 118, I'm not going to go through all of them. That's 90 elements. I'm going to show you the 14 that really matter. And the cool part of all of this is that as we look through all the elements, we can use them to understand the universe and history and technology. You know, hydrogen in the early universe, and carbon during life, and iron during the Iron Age, and uranium during the Cold War. Each of the elements tells a story about us, which is really cool. And so for each element, I'll be showing cool graphs and maps and diagrams to help us understand that element. And one other note before we begin is the ranking criteria I'm going to use. First is how important was it to the universe and to physics? So something like helium, important universally, but not that important on Earth. The second one is life. So how important is it for biology and chemistry? So something like carbon, obviously super important for life. And then the third one is how important is it for humans? You know, history and technology. How important is it for Homo sapiens today? Okay, let's begin. I'm going to open up the freaking thing over here. So let's show, here's our tier list. It's beautiful. What a beautiful piece of thing. We're going to start with number 1. Okay. And hydrogen. I mean, you cannot go wrong with hydrogen. It would be impossible to put hydrogen anywhere else but S tier. Hydrogen it's almost not an element, you know, it's a proton with an electron going around it. And that can go on to everything. In biology, it can go on to everything. With human stuff, it's obviously a part of, carbon, hydrocarbons and things like that we use today. So it's just the most important thing. It should be thought of less as an element and more of just like a protons and electrons to give to all the other elements. So it's super, super important. I think that hydrogen, I just want to show some things here. The other really important part about hydrogen is this is a graph on the right side here of the most common elements in the Milky Way galaxy. And so roughly speaking, you can see here is this parts per million. So 740 parts per million, or around 74% of all elements are hydrogen. So hydrogen is what everything started as. And then, 24% is helium, 1% is oxygen, and then the rest is the rest of the elements. And so it's like 3/4 of the universe. So if it's 3/4 of the universe, it's got to be super important. And by the way, you can see here, likely that some of these other ones that are high on this list, it's hard to be really rare and still be pretty important. So these other ones here are likely to be important as well. So that's one thing about hydrogen is it's most of the universe is hydrogen. The other, and you can see that here too, this is a relative abundance of different elements in the universe, and there's just another way, there's a log graph, so there's just another way to see it, and you can see how much hydrogen, helium there is compared to the rest of the elements. This is also hydrogen is such a beautiful thing. And you can see, I want to talk about there's so many things that you could talk about with hydrogen in biology, but I want to talk about the ATP synthase, which is this beautiful, look at this thing. This is a motor that charges our bodies. And so this is a motor essentially which produces ATP, and then ATP is like the energy currency of the cell. And so the way that this works is we have, for all life, single-celled life, for all multicellular life, plants and fungi and everything, and then also all single-celled life, bacteria and everything. everything runs either in mitochondria or around the cell. They run, you're pulling in hydrogen, and you're ripping it into two, and you're pushing the protons to the downside here, and then you're pulling the electrons to the other side, and then what you get is a electrochemical gradient where there are positive protons on one side of this membrane, of the cellular membrane. And then what our bodies do is that they pull those hydrogen protons through this motor, a literal motor. This is made of proteins, this is at the nanometer scale. And so it's pulling these protons through this motor, which spins the motor. And then by spinning the motor, it sticks a phosphorus onto ADP, turning it into ATP. And so it's kind of like charging up these batteries by running a motor. The glowing dots are the things that are flowing through this inner membrane space, turning this motor. So this is just an example of how amazing. So hydrogen pumps essentially are the main energy production system of the cell and of all life. And so there's trillions and trillions of copies of ATP synthase running in all life at all times. So hydrogen, that's one just example of hydrogen being so important. And here's, you can see it here. There's just another way to visualize that, where the hydrogen gets pulled through. This is just like the other view instead of this is the side view, but instead of 3D, this is 2D. And so you can see hydrogen being pushed up to the top up here. See how these arrows on the left are all going up, up, up. It's pumping hydrogen up. And then this final one, the ATP synthase, it pulls the hydrogen through, turning ADP with the phosphate into ATP. So that is beautiful. And we'll talk more about oxygen's role in that and stuff later. But I think this is just one small example of the role that hydrogen plays. So that is hydrogen. It is, it's 100% A tier, 100% S tier. And if you could, I would even put it into like S plus if I could, because it's just that important. Okay, let's look at helium now. Helium is interesting. Helium's interesting. Helium, I ain't got nothing wrong with helium. Helium's crazy. I think helium, if you think back to that graph from not this one, but this one, you can see that helium is 24% of all atomic mass is helium. And so helium, because of that, it's like, it is so freaking, I am going to delete this group, why not? So that means just the fact that helium is so numerous is pretty important. And I think that there's for chemistry, helium's weird because it doesn't really do any chemistry. It doesn't, if you think about helium, because it's a noble gas. And so if we look, over here, helium's part of this neon, argon, etc. It's a noble gas on the far side, aka it has a full electrons in its outer orbital. And that means that it doesn't make covalent bonds. It doesn't make ionic bonds. And so it can't do chemistry. There's essentially nothing on the right side here ever does chemistry. It just kind of hangs out as it is. And so helium, from a biological perspective, it's not very important. And then also from a human perspective, it's not very important. We have the balloons that you can make your voice sound funny and things. Maybe there was some helium gas that we used in like dirigibles and things like that to be big. So helium's kind of a weird, arguable one. I think the other really important thing about helium is it does alpha decay. And so there are two main types of decay in the world. There is beta decay, where you're turning protons into neutrons or vice versa. And that's very important for, solar fusion. But I think that there is alpha decay is the other really important thing, where when you have a big element, then what it will do is it will shoot off. So you can see here, uranium-238, it decays to thorium-234. It loses helium. So helium's getting kind of pumped out of the system. And so I think in that way, helium is very important. And so I think the other actually thing that I want to say about helium, which is cool, is the helium, the triple alpha process, helium fusion suns. It is, yes, nuclear fusion in the sun, and specifically I want to look for not triple, there's the triple alpha. Yeah, it is a triple alpha process. Okay, great. So this is the other super important thing that helium does, is it is if you look at this graph, this is us, when stars are doing fusion, they mostly shove protons onto each other to produce helium. Occasionally they do that faster through this C and O cycle, carbon, nitrogen, oxygen cycle. But then once they get big enough, then they do the triple alpha process where they create bigger elements. And so that's the other important part of helium, is that the only way you get bigger elements in the world is through the triple alpha process. And so let me show one other image of it here. Yeah, this image is a sign of just how important helium is. So you can see here's the proton-proton chain that I was talking about, where you are using protons to produce helium. Then there's the CNO cycle, where you're using CNO to produce hydrogen to do fusion more efficiently. But then the alpha process down here, it's taking helium atoms or carbon atoms, and then it is using them to then you're kind of shoving helium onto them and going up by even numbers, going from carbon to oxygen to neon, etc. And this is why there are more even numbers, why elements with even numbers, why their elemental composition, why there's more of them than odd numbers. And so this is a very important process. So all the elements get produced by pushing helium onto them. So helium is very important. It is, and so I think if I were to say what helium is, I think that let's don't ask again, delete group. So I'm going to say that helium, it's tempting to put it in B tier as a, because it doesn't do anything for life or humans, but I think I'm going to put it in A tier just because of how important it was for the first 10 billion years of the universe, because it's 24% of all elements are helium, and so 24% of all mass in the universe is helium atoms. So I think I'm putting it in A tier. Okay, now let's look at lithium. Lithium is interesting. Lithium is important. My instinct is to put it somewhere around B tier. I think that it is, I think that we mostly think of lithium these days as batteries, lithium ion batteries, and that is important. It was in the early universe, some of like Big Bang nucleosynthesis produced a little bit of lithium, but it's not that important. And biology, it's not that important. But yeah, for humans, it's pretty important. And so you can see the reason why it's important is because it has its outer orbital has just one electron in it, and so it can give and receive this electron very easily. And what that means is in a lithium ion battery, you can you have the lithium on the left here. You'll charge the battery, pushing the electrons off of it. The electrons will go to the other side. The lithium will go through the electrolyte and then go to the other side, essentially to catch them. And then when you are using the battery, then the electrons go back the other way, the reverse direction of this, through the battery and run whatever you're running, and then the lithiums go back to the left side to recatch the electrons over there. And so this is why, and lithium is great for this because it's so light. And so this is why it's versus salt, sodium, which we'll talk about later. Sodium ion batteries are good, but they're heavier. And so lithium is extremely important for that reason. It's becoming more important as electricity has become more important in the world. So you can see here's a lithium production graph too. This is just over the past 25, 30 years. And so in the world, we're producing 200,000 tons of lithium now versus it was 10,000 tons 30 years ago. And so we're mass producing more lithium these days, which is important. And it comes from, and blah, blah, blah. It's, more and more is coming from China, obviously. This Chile, it coming from Chile is pretty interesting. This is part of this, there's a triangle, the lithium triangle, in Chile, Argentina, Bolivia, near those salt flats down there. And so that's where they produce lots of lithium. And so that's kind of a place where there's lots of Chinese investment, et cetera, happening right now. So yeah, lithium, I think, is, because of how important it is for batteries these days. I'm not sure what percent of all battery, you could do some math where you say what percentage of all watts of all batteries is charged or output through lithium, and that would be a large amount. It's not as important as something like copper, which contains all of the which is pumping tons and tons of electrons through it, because lithium is only for batteries, not for wires in general. But I think I'm going to put it at B tier for now. Not quite A tier, but very important, especially today. So that's lithium. Now let's talk about, these next two, beryllium and boron. They're not that important. And they're not important enough that I'm even going to put them, I think I'm taking them as, I'm going to put them both in F tier. They are, part of this is because there's not that many of them in the that triple alpha process that I was showing earlier. It goes directly to carbon. It kind of skips over beryllium. So there's not that much beryllium in the world. There's not that much boron in the world. And so they're rare, and their properties aren't that helpful. So it is, they're essentially not really worth even talking about. I think, what do I even have here? Blah, blah, blah. Beryllium exists. Boron exists, but they're not that important. So let's keep moving on. And especially because what we're moving on to is carbon. Carbon. Oh my God. I think carbon, it's very clearly S tier. I think carbon, let me give a love letter to carbon for a second. I think carbon's my favorite element. Carbon, I love you, carbon. If I could marry one element, I'd marry carbon. If I could have a child and that child was only composed of one element, it would be carbon. If I could be reincarnated as an element, it would be carbon. I think carbon is my friend. Carbon is not my foe. It's a little bit of a friend of me because it can be used for good and for evil. But carbon is beautiful. Carbon is so nice. Let's talk a little bit more about why I love carbon. It's slightly important from a universal perspective, but as we get into more and more elements, they start becoming less important universally, because hydrogen and helium were the really important ones. But more just talking about biology and humanity now. So I think if we talk about carbon, and I'm going to show you a lot of graphs on carbon now. So let's do it. There's the first thing about carbon. Let's talk about biology and carbon. Carbon is, look at this beautiful all-world data graph. When you measure how much biomass there is in the world, carbon essentially, let me actually say this a different way. Carbon is 50% of all biomass. So if you think about your body, 50% of it is carbon. If you think about a tree, 50% of it is carbon. The rest of it's like hydrogen and oxygen, and then some nitrogen, and then some phosphorus, and then some sulfur, but it's mostly carbon. And so even when you measure, that's why this graph is so important, is because when you measure how much biomass there is in the world, the way people measure it is by saying how many tons of carbon it is. So that's interesting. It might even be 2x this, because carbon is only half of all biomass or whatever. But so this graph is just a cool graph. Almost all biomass is plants, as you can see here. And then some of biomass is bacteria. And then only a small percentage of biomass, 0.4%, is animals. And then of all the animals, it's mostly arthropods, aka like insects, things with exoskeletons, and fish. And then finally, here's humans. A little bit of humans, a little bit of livestock. So that's just a sign of how important carbon is that it's how you measure how much mass there is in things. And why is that? Well, carbon is what's called they make these beautiful carbon chains, They're called macromolecules, where you take a small molecule and you make a large sequence of them to chain them together. And those chains are essentially the source of information and the source of structure in this, and also the source of energy in all of life. So you can see the building blocks of life here. This is here are these 4 big macromolecules. On the far right side, you can see DNA. And so DNA is just a carbon chain. And it is, and that carbon chain is connected through these little hydrogen bonds, and it makes this beautiful alpha helix. And that's the information used to produce all of life and to produce all proteins. And so proteins are the second one. When you think about the protein folding problem and alpha fold and things like that, this is a weird picture of a protein, but proteins are a different kind of chain. And when you create a protein chain, we'll talk a little bit more about them later, these protein chains twist into weird shapes, and then those weird shapes do all of the structural roles. They do all the roles in our bodies. And so if you want something to do something, then a protein does it. So DNAs, which are a carbon chain, code for proteins, which are another carbon chain that folds into this certain way, and then that protein then does all these functions. And so the other one is a lipid here. And so this is if you think about cell walls are composed of, again, another carbon chain with and I'll show another picture of this in a second. It's a carbon chain with a phosphorus at the end. They're called phospholipid bilayers. And they're fatty because they just have carbon and hydrogen on them. They don't have any oxygen. They don't have anything else on them. They don't have any nitrogen. So they're not acidic, and they're also not basic. And so, these lipids form, they form the cells. Cell walls are made of lipids. And then carbohydrate starch. This is if you want to take if you think about, a carbohydrate, there's carbon at the very beginning there, and then hydrogen. It's carbon, hydrogen, and then oxygen. And so these chains of essentially like glucose is like a 6-carbon chain. That's called hexose. And those things are, they make up the energy for all of life. And so you have these 6-carbon chains that then get pushed into the Krebs cycle and things like that to run metabolism, and then you rip the hydrogen off of them to spin that ATP synthase that we talked about earlier. So these are the building blocks of life, and all of our bodies are essentially composed of these different kinds of carbon chains doing these different roles, providing structure, providing information, providing energy. So that's amazing. Here's another picture of these macromolecules. You can see here the beautiful part about carbon too is that all of these different, all the other elements they have to be talked about on this chart. They say, oh, here's a hydrogen, here's a nitrogen, here's an oxygen. Carbon is so important, and it creates these chains. It doesn't even get the letter C very often. It mostly just makes these little lines. And so you can see here something like, these nucleobases, these are RNA and DNA. That's a 6-carbon chain and a 5-carbon chain. And you combine them together you combine a nucleobase to make a nucleotide, aka DNA and RNA. Or here's what sugar looks like. This is you take this and this turns into these longer carbohydrate chains. The fatty acids we talked about, and then here's the amino acids, which are which have there's 20 different amino acids with different R groups, and they have different based off of those different R groups. That's why they twist up in different ways to do all the different functions in our bodies. So that is the macromolecules and what they're composed of. They're composed of monomers that make these long polymers. So that's that. The other cool thing about life is that it's all very similar. These carbon chains, you can see here's glucose. Glucose is mostly used as a energy carrier, but it can also be turned into other things. And so you can take glucose and you can turn it into, so cellulose is what plant cell walls are made out of. And so if you take glucose and you kind of stitch them together and futz around with some things, boom, it makes a cell wall. And so when you look at a plant, it's a bunch of cellulose. It's a bunch of these rings stitched together. And then chitin is what arthropod exoskeletons are made out of, like insect exoskeletons. And it's also what fungi are made out of. So fungi, their little hyphae are composed of chitin. And so this is similar to cellulose. It just has a little bit of nitrogen on it. And so that's pretty cool. That's what you can see how they're so similar to each other. The cell walls of plants versus fungi are very similar. And here's glycogen, which is, oh, wow, what a beautiful picture. This thing is a store of energy. So this is, when you think about glucose, this is a bunch of just glucose molecules arranged. When you're an animal, or when you're a plant, or when you're a fungi, and you want to store a bunch of energy, you store it in a big glycogen molecule like this, where you say, okay, I'm going to put this thing here, I'm going to put a bunch of glucose on it, and then when I need it, I'll kind of rip it off. So this is, hundreds or thousands of glucose molecules on a bigger glycogen molecule. So that's cool. I'm just talking about amazing stuff that happens in biology right now. The ribosome is the 3D printer of our cells. This is where, the DNA, but actually technically the RNA goes through. The RNA has a set of instructions on it, and it says, okay, I'm going to build this protein. And what that does is it goes into the ribosome, and and in comes RNA from one end. You look at the codons, a set of 3 RNA molecules, where it's like, oh, CGAT, which ones am I looking at? Oh, it's CCC. Okay, that produces this amino acid or whatever. That it's pushed through the ribosome, and then out the other end comes proteins. And the ribosome is cool because it is it's also composed of carbon, obviously, and it was likely one of the first things during the origin of life that was created. And the ribosome is when you look at this, the blue parts and the orange parts are slightly different, and one of them is RNA molecules that are being wrapped around, and the other one are just like a protein. And so this is, all of our bodies have tons of these little 3D printers in them, and they're composed of, again, strands of protein and RNA, but in this case, they're composed of in this way so that it can be a 3D printer for the rest of our body. So that's the ribosome. This is another picture of that phospholipid bilayer, where you can just see it's a bunch of these carbon and hydrogen chains. That's a long chain. It's a hydrophobic tail. It's a big, long, fatty acid tail that creates cell walls. So that's that. And then collagen. Collagen's funny. I have this weird picture here where, if you think about back to that image of this image of cellulose and chitin, these are what provides the structure in plants and fungi. And then you're like, well, what provides the structure in humans and animals? And I think that it's kind of a funny answer, but the collagen is the main thing that provides structure. So this is in our muscles and in our bones. They have a lot of collagen, and collagen is it's essentially it's just like a long string that wraps around itself. It's just a protein that is, the other ones are less flexible, chitin and cellulose, because if you think about that, it's like exoskeleton is very kind of hard and brittle. Plant walls are hard and brittle, and collagen is more, it can, our muscles can move around and stuff more. So, but I just want to say collagen is what animals are, what our structure is mostly composed of. This is another amazing thing, which is, so if you look at, so now let's talk about, so that's some of the role of carbon in biology. Is I just wanted to show at the molecular level, what are the important roles that carbon plays. And as you can tell there, carbon it's the chains behind all of life. And I think I want to before going to humans, I want to talk a little bit about the other roles that it plays in life. So let me show these images too. The other thing that it does is this is metabolism. So if you look at, here's this fun image of all the metabolic pathways in the body. And so this is when you take, this is the urea cycle. So this is uric acid and your P. And here's the citric acid cycle. This is the most important one where, if you think about metabolism, and so let's exit this for a second. This is the citric acid cycle. And what the citric acid cycle does is it essentially takes a 6-carbon chain, citrate here, that's why it's called citric acid, and it pulls off over time. Each new carbon here gets, if there's 6 at the beginning here, the little dark things with the C's are carbons, over time it becomes 5 down here, and then it becomes 4 with succinate, and then it becomes 3, and so, and then it becomes, and it goes back down to, so you're essentially taking a 6-carbon chain, you're pulling carbon off of it, and when you pull off a little bit of carbon, you go from a 6-carbon chain to a 4-carbon chain, and as you do that, you are spinning that, you're essentially running ATP synthase, and you can see it's producing energy in different ways here because you're pulling off some carbon, but also some oxygen, some hydrogen, and then you're using that oxygen as an oxidant in the electron transport chain, and you pull the hydrogen, it pushes those protons above you're pulling the electron down towards on NAD and NADH or whatever, and you're pulling as those little electron characters, and you're pulling you're pulling the electrons down, pushing the hydrogen up so that then you can keep that electrochemical gradient and then pull it back through later to produce ATP. So you're kind of like pulling off. This is how, when you have those glycogen stores and you have glucose, and you have the glucose or the citrate, these chains, those things then get they get turned into energy in this manner through the citric acid cycle. So all of the citric acid cycle is, and I could say more on this and why it was, when you think about the origin of life, probably what happened at the origin of life was actually just, it was just the citric acid cycle at the beginning. This was a natural cycle of carbon, oxygen, and hydrogen where it was producing, especially when it was done in reverse and blah, blah. I could say more on this, but I think there's this cycle was, especially the reverse version of the cycle where you're taking 2 carbons and you're adding carbons to it, breaking them into pieces, and then that produces a feedback loop where you start to then do this a bunch where you're taking more and more carbons, adding them on, and then before long you have a bunch of these cycles running. Metabolism is the core of all humans. It is what runs energy in our cells. It's what provides us with ATP, and it too obviously it's a very, very simple. If you think about some of those other carbon chains, something like proteins or DNA are very complicated. They have nitrogen on them, they have phosphorus on them, they sometimes have sulfur on them. They're very complicated. These are the simplest carbon chains that exist. They're just 2 to 6 carbons, and they are and they run all of metabolism. And so this thing has been hyper optimized over time because you want it to, because it's running all the time, and so you can't have it be too inefficient. You have to have it be very, very efficient. So this is the citric acid cycle. It's really cool. Other parts of it turn into all the other parts of the citric acid cycle turn into everything else. And so ketoglutarate and all these things, they turn into amino acids. They turn into sugar stores. They turn into lipids. So that's what this thing is. It's very, very cool and very, very important. And check out either Eric Smith or Nick Lane if you want to learn more about the citric acid cycle. So that is, okay, now we're back to this. So I think that's the biology side. Carbon chains are the foundation of everything, and that's cool. And they're the foundation of all biology, and that's why 50% of our bodies are carbon. And you start with these smaller molecules, like the citric acid cycle, and then you get increasingly long ones that turn into these longer sequences of macromolecules like proteins and lipids and RNA and DNA. And so that's carbon. Carbon's very cool. Human-wise, carbon is also super, not just biology, but in terms of our technology, in terms of the history of humanity, carbon is also really important. And so let's start in the past, which is, in the past, when you think about people call it the Stone Age, before we started farming and when we were just hunter-gatherers and, Homo sapiens and Homo erectus and stuff. And that's, calling it the Stone Age is reasonable, but you could also call it the Wood Age or the Carbon Age, because everything that we produced back then was made of carbon. These are our little houses were made of carbon. Our boats were made of carbon. Our spears were made of carbon. And some of these things you'd put rocks on them and whatever, but it was a carbon-based. All of our technology initially was built out of carbon. So that's, carbon played a very important role at the beginning, and then over time, the thing that I want to show here is, so today it also is also a very important role. So this is a cool image of the fractional distillation process of creating fuel. And so this is when you're taking fossil fuels, you're pulling them out of the ground, you're pulling crude oil out of the ground. You can see crude oil on the left here. And then what you do is you heat up that crude oil, and there's a fire underneath here, and the fire, it essentially distills the crude oil into different length carbon chains. And so when you think about, at the bottom, you have these like heavier oils, like, waxes and polishes, lubricating oils and things like that. And then higher up, then you get so these are solids down here. Then you get some liquids in the middle, petrol, gasoline, whatever. And at the top, you get gases. And so that is, and you can see here's the, they're saying how many carbons are in each of these chains. So this is C1 to C4, gases. And then here's C5 to C9, naphtha or whatever, C5 to C10, petrol. Down here, it's like these bigger fuel oils are C20 through C70. So those are really long carbon chains. And you can see, here's when you think about all the gas that exists in our world these days, it's produced in this fractional distillation process, and it is these are just the names of the formulas. So monkeys eat purple bananas are these first four, MEPB, and then you get into normal numbers: pentane, hexane, heptane, octane, etc. And so when you think about methane gas, what is methane gas? Well, it's CH4, and if you have that methane gas and then you light it on fire, then it for various reasons, it produces energy. With the oxygen-carbon bonds being better, it produces CO2, and then it produces water, H2O. And then a similar thing, there's propane. When you imagine propane tanks, they are made of a carbon chain with 3 carbons long. Butane is 4 carbons long. And then 5 through 8 are gas, when you think about gasoline. And so something like, when you say high octane fuel, this is what, for like race cars or whatever, it means fuel that has lots and lots of octane in it, versus ones that have more heptane or whatever. And so, because the octane has more energy. So these are, I just want to share with this as a way to say that this is all of the, when you think about how important carbon chains are, biology produced all of them. All those creatures died over the last, hundreds of millions of years. They went to the ground. They made fossil fuels. We found the fossil fuels. We pulled it out of the ground. We are then now distilling those fossil fuels into different length carbon chains and then lighting them on fire for different uses. So that is another thing why carbon is so important. And obviously, what that leads to then is this CO2 concentration, because when you are lighting these hydrocarbons, which doesn't have any oxygen in it, it's just C, carbon, and hydrogen. When you light those on fire, and you produce CO2 as a byproduct, and then you get this massive increase over the last 200 years of atmospheric CO2 concentration. So that is carbon. And one other note on carbon is in addition to the structures of, carbon's important because the walls, some of the walls behind me are made of, carbon 2x4s made of wood, but also these are plastics. All of plastics are made of carbon too. So when you think about a plastic is a carbon chain. It's another carbon chain, but instead of produced by life, it is produced by humans. And we we stick them in these, the polyethylene is CH2, and you stick them in these big chains. Polyvinyl chloride, you put a little chloride on it. Polypropylene, you put a little CH3 on it. So you're kind of adding, by creating these chains in different ways, you produce harder plastics or softer plastics. And so plastics, everything around us is some of it is concrete and some of it is steel, which we'll both get to in a second, but a lot of it is carbon, these carbon chains that are produced. So that is carbon. Wow. Carbon is amazing, and carbon chains are really cool. And I think that if you were to look other places in the universe, you would see, like when you look at other life, almost certainly it's in water. And then you can say, well, if it's in water, okay, then what does water allow? Water allows carbon chains to form. And then those carbon chains explore their design space and find, metabolism. And then metabolism explores, it's a reinforcing feedback loop that produces, it's the first autocatalytic cycle that produces, more and more carbon chains and carbon cycles, reverse Krebs cycles. And then that starts to explore its design space, and it starts to find longer molecules, and it starts to put nitrogen and phosphorus on them. And so I think and then eventually you get to DNA and RNA, and then you get stuff like the ribosome to produce, to repeatedly produce high value carbon chains. And then you start to get cells and things like that. So you can see how all of that is. So this is to say, I think that we have that on Earth, but also if you were to look at other planets in the world that have life, almost certainly it's carbon chain based. Okay, so that's carbon. Total S tier element. Hope I didn't spend too much time talking about it. Now let's talk about nitrogen. It would be hard to put nitrogen anywhere besides A tier, I think. When you think about this periodic table, so these, you can see the organic elements are here, and it's hard to, for a lot of these are the ones that are important for life. And so that's why they're so freaking, so a lot of them are going to be important. And so nitrogen's cool. I think nitrogen is probably, sorry, I was sharing something without showing it. These are the, organic molecules, the organic elements, and so these are the ones that make easy covalent bonds with each other, and these ones are going to be very important because they're all part of life. So that's why nitrogen is almost certainly going to be in the A tier, because it's an important organic element. Yeah, and so nitrogen, when you think about nitrogen, you can see it being on some of these macromolecules. That's why nitrogen it's important, because it's a core building block, And so you can see here on DNA, nitrogen is a part of the DNA. It's also it's not a part of fatty acids or sugars. Those are just carbohydrates or hydrocarbons. But amino acids also have nitrogen. All of it has amino acids have an amine group, which is purely nitrogen, and then also a lot of the R group of amino acids, some of them have nitrogen as well. So nitrogen it's essentially, if you go back to this periodic table thing, you imagine these organic elements, carbon and hydrogen start to form these chains, but nitrogen provides a little bit of spice. It says, okay, we're going to, it can be a little bit acidic. It can essentially be like a little unique element that you can put on there that starts to play different roles within biochemistry. So nitrogen is important. It is, it's, and this image is showing these like electron carriers, NADH, electron/proton carriers that work in the electron transport chain. And I guess the reason why I want to show this is because you can see that they are, nitrogen starts to play the role of, and I think, let's refresh this thing. It's a kind of a cool thing. This is an image of all of these B vitamins. And when you think back to the Krebs cycle, that Krebs cycle is running in all of us all the time. And at the beginning, when it was running in reverse, when it was producing carbon, when it was taking energy as input and producing carbon, versus these days it mostly runs in forward, where it has carbon as input and then produces energy. This when the Krebs cycle is running, it needs to get stuff needs to get brought to it, and so the things that get brought to it are things like carbon gets brought to it, or oxygen gets brought to it, or nitrogen gets brought to it. And the B vitamins are essentially the vitamins that are responsible for helping metabolism run better. And so you can see this here, the B vitamins on the left, B1, B2, riboflavin, and niacin, and biotin. You may have seen these on the back of a nutrition panel. Here's what they look like. They're these, some of them are smaller, some of them are bigger. A lot of them have, almost all of them have nitrogen on them. And the role that they play is, this says decarboxylation reaction. This says carboxylation reaction. So that's either putting on or pulling off a CO2 molecule onto that course that core Krebs cycle, and so the citric acid cycle. This one, pyridoxine. This one is amino acid group transfer. So if you're pulling, you want to push on or pull off a little amino acid, you can do that. And so the reason why I show this is because I think that as part of that, when you think about that initial core cycle, you need to pull and push things onto that core cycle, pull and push carbon and oxygen and nitrogen, or you can pull and push electrons themselves with NADH and NAD+, and those are often, that role is done by these little tiny molecules that have nitrogen on them as well. So that is a little bit on nitrogen. I think you can see here at the macro perspective, nitrogen as a fertilizer. This is why, with the Green Revolution and the Haber-Bosch process, being able to turn ammonia into fertilizer. Half of all nitrogen in our bodies is from the Haber-Bosch process, this industrial process that produces fertilizer. And what it does is it produces nitrogen. And so you can see here over time, this is the amount of nitrogen produced, total nitrogen produced per year. Almost certainly just per year, yeah. And we're producing a lot of nitrogen per year. It uses a bunch of energy. And so you can see here's a picture of how much these are annual carbon emissions per year. And you can see within industry, producing carbon, producing steel, producing cement. You can see here that chemicals, which is essentially ammonia, aka doing that Haber-Bosch process, producing the fertilizer, is 14%. If you think about all emissions from industrial things, a lot of it comes from iron production, a lot of it comes from steel production. That's like 30% for each of those, but then 15% comes from the production of ammonia and fertilizer. So yeah, the nitrogen is very important, and as one of those core little pieces of building blocks, both proteins and DNA require it. And so, yeah, I think it's almost certainly A tier. I think it would be hard to put it in B tier. So I'm going to put an A tier. So that is nitrogen. Let's talk about oxygen. Oxygen's funny. I think that oxygen, oxygen is an important element. It's almost certainly A tier or S tier. I think that from a pure, it's 20% of our atmosphere is oxygen. the world got oxygenated recently, with cyanobacteria and producing the great oxygenation event. That's a great oxidation event. And it is, this is when we first started to produce oxygen. And so this is billions of years ago. And so the world was an anoxic environment before this. And it was, and then the first photosynthesizing bacteria came around. They produced, that was the first, cyanobacteria. They produced 2 billion years ago. They started to, they took hydrogen and they took H2O and they ripped the hydrogen off of it, leaving oxygen as a byproduct, which is really crazy. And by doing that, they rusted all the steel in the world, they oxygenated all the oceans, and then once it was in all those things, once it was in all the rocks and all the water, then it could go into the air. And so it started to go into the air and it started to go into the atmosphere. It killed everything. And then over time, over a billion plus years, the boring billion plus, then it's, 500 million years ago, around the Cambrian explosion, the world became more oxygenated. And then that allowed animals to be, these new multicellular animals, to have enough energy to actually run the electron transport chain and to run their metabolism more efficiently. I think it's like 10 to 100x more efficient to use oxygen as an oxidant than it is to use other things. So yeah, I think there's so oxygen is very important, and everything had to update to using oxygen. Oxygen is a very clear sign of life on other planets if you end up using it. So yeah, I think given how important, and this is just an image of, that electron transport chain, and oxygen is the final electron acceptor and crap. I think that I'm going to say that oxygen, you could put it S tier, you could put it A tier. It's very close. I'll leave it at A for now, though you could easily put an S if you wanted to. It's really important for, oh man, yeah, it's close. I'll leave it an A tier for now. Okay, so now we get to fluorine. Fluorine is kind of a funny one, because fluorine and chlorine and bromine, these are elements, they're halogens, and they just super easily combine with these earth metals over here, because, if you think about sodium, NaCl, that's sodium, and chlorine, that's salt. And so they just, because sodium has one extra electron, and because chlorine and fluorine really want that one extra electron, they form bonds super easily. And so it's very hard to find fluorine in the world because it's so reactive. If you find a fluorine without that its final electron orbital filled, it wants to fill it really fast. So I think fluorine is, it's funny because fluorine's kind of important as a lot of those fluorine and chlorine are important because they can be reactive. They can be a good oxidant. They can pull things. They can essentially do molecular cleaning. And so that's why fluorine for our teeth, the old RFK thing of fluorine in the water. I think that fluorine is probably D tier, though. It's not nearly as important as chlorine. Chlorine, which we'll talk about later, it's less reactive, it saved more lives, etc. So I think fluorine's D tier. You could put in C tier if you want, but it's not that important, but is slightly important for keeping our teeth clean. Neon feels like it's also in that D tier. Maybe you could put it in that F tier, where it's like, because it's a noble gas, it doesn't do any chemistry with anything else. And it, produce some of those neon lights and stuff, but they're rarely used these days. So I'm going to put an F tier. These ones that are in this far right side, neon, argon, it's a hard sell. It's a hard sell to put you higher up. Sodium's important. Sodium, it's tempting to put it in A tier. It might be B tier. It's pretty close. Salt has been very important in, so salt, you can see here is a, salt's definitely, let me follow up for a second. Salt is 100% in A tier. Salt is, because biologically speaking, Salt is it does this the sodium potassium channels. These are the channels that they keep in our neurons and in our muscles. These are the sodium is used essentially to keep a resting electric potential, and so you're pumping sodium out of the cell. You're pumping potassium into the cell, and you're essentially getting too much plus on the outside, and then you get too much minus on the inside, and so you're keeping that electric potential. And so, yeah, this is how brains work. It's how all nerves work. It's really important. And so, in biology, it's super important. It's why we need salt. It's why, So it's super important from a biological perspective, and then also from a sodium-ion battery perspective. This is likely to become more and more helpful over time. You can see here this is similar to the lithium image from before, but instead of lithium moving in between the anode and the cathode, you have sodium moving between. And again, it plays the same role where it has that extra electron on the end, and and so it can easily give or receive that electron. And so that's why it has an important role in biology. It's also, and then we'll see over time, as we mine more and more lithium, how much lithium is there going to be? Do we need to use more sodium batteries? They're good, but they're heavier, because sodium is heavier. So we'll see, but CATL and others are making really good sodium batteries. So I'm excited to see us use more sodium batteries over time. So yeah, so this is to say, I think that sodium is, and then salt, just in the history, I didn't add this images of this, but salt has been a very important, it was very important for the history of humanity. And, when you think about civilization and salt trades and giving and receiving salt on foods for both, also to cure it, to leave it for longer so it doesn't go bad. So salt's pretty important. It's important enough on enough categories that I'm going to put an A tier. Okay, Magnesium was a funny one for me. I think I'm going to put in B tier. Initially, I was like, I don't really know. Magnesium's not that important. Maybe C tier or D tier. But after doing some more research, magnesium is surprisingly useful. It is the third most commonly used structural metal, following iron and aluminum. That's crazy to me. That's crazy. Third most commonly used. The other thing is, it is the main in biological systems. It does have two important roles. So the one that's more clear is in chlorophyll. Chlorophyll is a molecule that has it's got this magnesium in the middle, and chlorophyll is essentially a synthesized reductant. And so this is the thing that when you think about those cyanobacteria, the main thing they did back in the day, the main invention that they had in order to produce to do photosynthesis was they produced chlorophyll, which is this magnesium metal that is kind of contained in this way. And it's a synthesized oxidant. Because it is oxidizing others. Yeah, it gets oxidized. It reduces others. I'm not sure. And so what it does is, instead of having something like oxygen down there to pull, because that's what most in the past, you'd have oxygen, sometimes you've had sulfur to run the electron transport chain and to be the terminal electron acceptor, and that made sense. But with chlorophyll, now you were able to have H2O and to bring H2O as an actual, and to pull the H2 off of it, which had never really been done before, and we were able to do that with chlorophyll. So chlorophyll's very important from that perspective. It is and the other reason why, and magnesium is the core metal within chlorophyll. The other important thing is that almost all ATP has magnesium in it. As it says here, what is called ATP is often actually MgATP. For example, ATP, the main source of energy in cells, must bind to magnesium in order to be biologically active. So yeah, magnesium is like a funny metal where it is one of the first. It's like not that heavy. it can, and so it's one of the first metals that can be kind of used and kind of, it's like a heavier element that can be used for biological processes. So I think that magnesium, it's the third most used structural metal. I don't really know why yet. That's a Reese to do, but I think it has to be, arguably it could be A tier, honestly, but I don't know enough about it, so I'm going to put it in B tier. So that's magnesium. And yeah, now let's talk about aluminum. Aluminum feels C tier to me. It's ain't nothing wrong with aluminum. It is a light metal, you know. It's you can see it over here. It's light, and it's used for planes. It's used for cans. It's used for aluminum foil. It's used when you want metallic properties, but you want it to be pretty light. So aluminum's good. It takes lots of energy, and so when you have during like the Russia-Ukraine thing, when Europe had less energy from Russia, all their aluminum plants shut down because they had less energy going to them. So yeah, aluminum's interesting and kind of important, but not that crucial. Silicon, I want to put silicon in S tier. I think you could put it in A tier if you wanted to, but I think that silicon is, it is the source of these new brains that are coming into the world. It is the substrate for artificial intelligence. So for computers and for transistors and for artificial intelligence. So I think it's S tier for that reason. It's not that important biologically, but it is a crucial thing for AI. And also the interesting thing with silicon is that silicon, when you think about the crust of the earth, these are I think this is by weight, how much of each element there is. And so most of the crust is silicon and oxide. So when you think about sand, that's silicon dioxide, and it is SiO2. And so that's a funny thing as a side note. When you see silicon here, you're like CO2, carbon dioxide is the thing right above it. Silicon dioxide, carbon dioxide is a gas. Silicon dioxide is sand. And so it's, so most of the crust is silicon dioxide. That's called a silicate. And so when you think about most rocks, that's the other reason why silicon is totally S tier, is because most rocks are just these silicon crystals. Here's, you can see SiO4. This is a silicate tetrahedron, which is you can see it forms these little triangles and these little tetrahedrals with SiO4, and they get connected to each other. And sometimes they have potassium in them, and sometimes they have other things. And you can see here, these are, when you think about all the rocks in the world, what they're made of, what is magma made of, everything, it's all silicon. And so the different names of all these different things are just different forms of these silicon tetrahedron patterns. And so the one that I was just showing here, I think this is feldspar, and it is that's why they have this three-dimensional structure. But then a lot of the other ones, if you think about something like a mica is, if you go into the world, or something like some of these quartzes, I guess the quartzes are down here. Quartz is just pure SiO4, by the way. So it's like a feldspar, but it doesn't have these potassiums in there. And mica is just a sheet. So it is a sheet of, I think it might be a sheet of just SiO4, of silicon oxide. So all of these sandstone, limestone, all these things are composed of these different kinds of, essentially the earth was like, what are all the different ways that I can, I have all this silicon oxide to mess around with. What are all the ways that I can produce rocks from it? What are all the different three-dimensional lattices that can emerge that are structurally sound and that exist stably through time? And these are what they are. So these are all the main rocks in the world, and the main minerals in the world. And so that's why silicon is important. Here's all that feldspar that we were talking about. This is all silicates. And you can see only 8% are these non-silicates. And so those are, so almost everything is made of silicon. So it's important from an earth perspective. There's tons of sand. Most things are sand. And then it's also important from a technology. Actually, before we get to full technology perspective, the other thing that's interesting with rocks is that in sand is because if you want to think about, that image from before, I was like, most of the wood in the world, before the Iron Age, before the Bronze Age, there was, it was the pottery age, essentially. And so you can see, here's a map of, this is after we got farming. So, we were hunter-gatherers. We were using mostly, carbon-based, wooden spears and wooden huts and stuff. And then we started to make pottery. And so these are Eastern European, these are EEFs, Eastern European farmers. Yeah. And so this is roughly, 10,000 BCE to 3,000 BCE. The name of all these little groups are, we define them by their pottery that they make. And pottery is just dirt, and dirt is just sand, and sand is just silicon oxide. And so these groups are a little bit later, the Yamnaya, the corded ware, the bell beakers, and these are essentially pastoralists. These are like the original, Genghis Khan, the original Mongols kind of, but this is around 3000 BCE, and they pushed into Europe. And when you look at these groups they're defined by their different kinds of pottery they make. The bell beaker group, the pottery looks slightly different than the corded ware group. And so, I think that's another important piece of silicon, is that it started to, one of the main things that fossilize are these pottery things, and dirt was one of the main things that we used to build our homes and to make our cups and to make our bowls. And so that's another reason why silicon is a totally S tier element. We don't need to go too deep into how transistors work, but they are semiconductors, which is really cool. Most things like copper are a conductor where you have an electron near the conduction band, and it creates an energy band, and the electrons can flow super freely, which is amazing. And so if you charge it on one end or the other, then the electrons flow from one to the other super easily. On an insulator, these are things where they don't have the outer electron orbitals doesn't easily give or take electrons, and so it's hard for electrons to flow in something like rubber or whatever. But then a semiconductor, it's close. It's this thing where if you add enough energy to it, then it can actually start to conduct. It can actually start to move electrons around it. And so this is there's more to say here, but I think there's something like silicon is a good semiconductor, and it is, it's not like copper, but it's not like rubber, and it can be this thing where it can hold charges. So that's silicon. I think silicon's S tier. It's been, if you were to think from everything up into the year 2000, or to the year 1950, silicon would be like, C tier or B tier. But given AI and everything, silicon is given it that it is the substrate for intelligence, for future intelligence, totally S tier. Okay, so now let's talk about phosphorus. Phosphorus is interesting. We're back to these organic elements now. We just left silicon, and now we're back to phosphorus and sulfur. I think phosphorus is kind of like nitrogen in that it's important, but it's one click. There's less of it, and there's and it's not as important as nitrogen and oxygen. So I think it's got to be, but it's part of ATP. It's part of DNA. It's essentially just as important as nitrogen, but I think there's a little bit less of it. So I'm going to probably put it in B tier. You can see here's the role phosphorus plays. It is in DNA. It provides this amazing backbone, this sugar phosphate backbone. Here's the P, where you have on each side, essentially it's kind of like the back of the staircase or whatever is made of phosphorus. It is part of an ATP. It's the main bond in ATP. So it provides structure sometimes. It provides energy, a high energy bond sometimes in ATP. It provides compartmentalization. And so it provides this, it's the phosphate is the kind of the head of these phospholipid bilayers. So that's very important. And so, I think you could, if you wanted to, you could put phosphorus in A tier, and it's tempting to do so. I don't know. I'll put it in A tier for now, actually, because it's essentially as important as nitrogen, oxygen, and sodium from a biological perspective. Okay, let's talk about sulfur. Now, sulfur, I don't see sulfur being A tier at all. It could be B tier, but I think it's probably C tier, honestly. Sulfur is cool when you, it is some amino acids have sulfur in them, and sulfur, it has, and the cool thing with amino acids is that, these proteins, they form these different structures. And so, the different structures you have, these, based off of the way that all of the different little groups are interacting with each other and the hydrogen bonds and stuff like that. And so there's some like simple structures like these spinning, these are called alpha helixes, or these beta pleated sheets. And then the other thing though that it can do is you sometimes have these hydrophobic interactions where you get these little cores, a hydrophobic core in these proteins, and that can play a different role. So this disulfide linkage, though, is another one of the kind of tools that proteins have in order to change their structure. And so this disulfide linkage, which you can see here, this is in these keratin chains. It's pretty important. And our hair is composed, I'm pointing at my own hair as if I had any. Our hair has keratin in it. Hooves have keratin in it. And it is... it makes it like kind of like a strong bond there, a strong disulfide bond, which is why hooves are strong, which is why hair is strong, and why if you burn hair, it smells like sulfur. So that's kind of cool. And so yeah, sulfur it's interesting. It's not I'm not opposed to sulfur, but I think it's probably C tier, not that important. Chlorine might honestly be A tier. It's either A or B tier. It's hard because a lot of these are organic, things up here. But I think chlorine, I'm tempted to put it into A tier. It's similar to fluorine as I was talking about before. But if you think about chlorination saves so many lives. So there's this cool image that shows 50 inventions that saved, that formed the foundation of modern life expectancy. And there's like how many lives were saved or whatever. And then you can see it started way back here. Here's toilets were invented in 1850 or whatever, and that saved lots of lives. But one of the things here is water chlorination. To 175 million lives. Water chlorination killed all of cholera. Cholera used to kill so many people. And so chlorine so the fact that most water systems that we're all being kind of have chlorine in them and that we're kind of being pumped full of chlorine these days is pretty important. So maybe it's not quite A tier, but I will put it at B tier because it is an important disinfectant. Okay, so now argon. I'm sorry, argon. You're just going to go into the F tier. Another noble gas. Don't care. Potassium. It's kind of like sodium in these pumps, but just slightly less important, and yeah, I don't really see it. Maybe it's even C tier. It is part of these sodium potassium pumps, but sodium has all these other roles. So yeah, I think I'll put it in C tier. Calcium is interesting. Calcium is important. Calcium is it makes all of our bones. It also in mollusks. It makes everything in. Oh, dude, calcium is actually totally A tier. So yeah, calcium. Let's look at calcium for a second. It's part of cement. Okay, so that is one important thing. Is if you see cement and 60% of cement is lime, aka CaO, and so. And that's why lime comes from limestone. Limestone comes from the shells of dead, 100 million years ago. It's essentially a fossil fuel, but instead of fossilizing, hydrocarbons, you're fossilizing calcium, and then from the shells of these old mollusks and things, and then from those shells you get limestone, and from limestone you get concrete, and then concrete builds our walls. So yeah, so calcium is important from that perspective. It is if you look at how this is a scale of, actually, let me show you this image. This is only recently did, biomass, as I showed you earlier, is roughly, 1 trillion, or it's a teraton. It's a lot of weight, all that carbon out there. And only recently did anthropogenic mass pass it. So you can see here, we're just now passing, there's more concrete, there's more stones, there's more steel out in the world than there is biomass. And you can see when you look at this graph, a lot of the percentage of this is concrete, this blue out here, or the dark blue, and then aggregates, which are, I guess, just gravel. That's just like silicon oxide. So, but concrete's an important one. And so, if you look, here's this, 550 gigatons, roughly half of all of anthropogenic mass is concrete. It's the most frequently used building material and the second most used substance in the world after water. So, so it's important. So it's kind of at that level of silicon in that way, and that it provides structure for our buildings and much of humanity. I think that the other thing that and again, concrete's composed of calcium. The other thing that calcium does is it is helpful for our own bones, but it's also helpful for mollusks and crustaceans. And so when you think about coral loss, and when you think about why ocean acidification is bad, it's because ocean acidification essentially stops these little mollusks and crustaceans from making their shells. And so you can see here, this is, I don't know what, how much ocean acidification is here, but if you have a little bit of it, then you have, 40% less calcification, or, 30% less calcification, and then people die. So that would be one of the main impacts of climate change, is ocean acidification, and then less calcification for these sea creatures. And so, calcium's, it provides an important structural role in biology. It does those, and then it provides an important structural role in human life through concrete. And so I'm going to put it at A tier. Yeah, so now scandium. So now we're getting into, so we just hit up, here's calcium. And so you can see, we had these important batteries, lithium and lithium and sodium up here. We had, calcium as an important, all the things we just talked about. And now we're getting into these metals, these transition metals in the middle here. And so I think that transition metals are fine. They are, iron obviously is super important, but some of them, scandium and, so scandium, not important, F tier, and then vanadium or whatever it's called, not important, also F tier. These other ones, titanium and chromium and manganese, are all super important because they are, they make like stainless steels, and they make, like chromium. Chrome is like a stainless steel, and so these things help with corrosion resistance, and they help turn all this steel that we produce in the world, they help make it stronger in different ways. And so you can see here's an image of, let's see here, here's roughly how that works. This is steel. So steel is essentially iron where you leave a little bit of the carbon in it, so that, because if you just have iron, it's kind of too brittle and whatever, but if you have the carbon in there, it cracks less easily and stuff. And so similarly, that's roughly the role that titanium and chromium and manganese play. And you can see here, in terms of all the metals we mined, almost all of it is iron, 2.6 billion tons. And then 10x less than that is the rest of these industrial metals. We talked about aluminum before. That's a lot of aluminum. Maybe I should put, C tier's fine. Maybe it should be A tier, or maybe it should be B tier. You know what? We'll leave it here. But you can see here's chromium, here's manganese, and here's titanium. And so titanium, these are part of, so they're important. I think that they are. And then here you can see there's another random image of, for combining chromium into these iron complexes, here's how to make better, stronger steel. So it's, so this is to say, I think they are all, I'll put aluminum into B tier, and then I'll put all of these. You could put titanium, you could argue which of these should be higher or lower than the others, but I think C tier for all of them seems relatively fine. Okay, so now, iron. Iron's got to be S tier. It's totally S tier. It is, yeah, I mean, it is. Let's talk about why iron's important. Biologically speaking, iron is, let's see here. So first, I guess, before even biology, let's talk about in the universe how much iron there is, and on Earth how much iron there is. And you can see here the crust of the Earth, the core of the Earth is mostly all iron. So deep inside our Earth is iron. The core, the mantle. Only once you get to the crust does it become these silicon oxides. And so when you think about the whole bulk Earth, it's still like a third iron. So iron is what our Earth is made of, which is very important. I'm going to sneeze. Maybe not. No. Okay. The iron. Why is iron important? Why is there so much of it? It's the only, before neutron star mergers and supernovas, it's like the heaviest element that you can get, that you can make in stars. Because when you keep shoving these heliums onto things, only with iron, you have the right proton to neutron ratio where the, essentially the strong nuclear force velcroing all those protons and neutrons together is still higher than all the protons trying to push away from each other, the electromagnetic force of all those positively charged protons trying to get away from each other. So iron is important for that reason. You can see this is the relative abundance graph again. You can see iron, there's a lot of iron. There's almost as much iron as these earlier elements, even though it gets produced much, much later. So there's a lot of iron in the world. Iron, biologically speaking, has a couple of important roles. Probably the most important metal. Yeah, I mean, magnesium is important. Sodium's not a metal, but it's also important. But it's iron. The role it plays in our bodies, yeah, it's so important. One of them is in this in the electron transport chain. Iron essentially, our bodies essentially have this wire that they make through these FeS2s, which are called ferredoxin, or these iron sulfur clusters. And when the electron is essentially jumping, we essentially have an electron jump between them. Kind of like a wire. And so it's, a thing that all of our bodies use iron to, as the wire behind the electron transport chain. So that's very important. It's also the hemoglobin molecule. So if we think about our red blood cells and we think about one of the proteins that we have is hemoglobin, and it's a really big molecule. It has these 4 different hemes all attached to each other, and what they do is they have these oxygen mitts, because oxygen's a pretty big. Oxygen is a large molecule in and of itself, and so it can oxidize other things, and so it's kind of dangerous, and so you need like a big molecule to hold on to it, and so iron does that. And iron, and so hemoglobin is, when you think about our bodies, iron is really, really crucial, and you get anemia or whatever if you don't have enough iron, because then our hemoglobin, you can't produce hemoglobin, and you can't have these little, then your blood essentially won't be oxygenated well enough. So that's another reason why iron's important biologically. And then obviously in the course of human history, iron's been very important. It's the name of one of the ages. So we had the Stone Age back in the day, the Bronze Age, which we're talking about in a second, and then the Iron Age. And so getting iron was a very important thing. There's the Bronze Age collapse, and then we got iron, and iron then, all future civilizations after that point, the Neo-Assyrians, everything in India, everything in China, the Egyptians, the Greeks, everything started to become, we started to be able to produce lots more food by making these iron plows and these iron axes, and we also started to be able to fight each other more with iron swords and all of that. And so we switched into a new kind of paradigm of both food production and weaponization as a result of the Iron Age. So iron, very, very crucial here. And then here back to this great image from before about industry. And how, we were talking about chemicals from before, and ammonia, we were talking about cement from before, and how much energy that uses. But iron, the production of iron uses 30% of all industry gigatons. And so we're producing lots and lots of yeah, the iron and steel production process produces lots of carbon. Why is that, by the way? It's because you push a bunch of, there's another image down here, which is, as you can see, it's yeah, the heat, it just, you have to be so hot in these coke furnaces and whatever in order to produce iron and steel. So that is yeah, iron is crucial to our modern day. It's crucial for all steel. Here, I guess here was another picture. All these random groups during the Iron Age were, yeah, these were these Iron Age cultures that were, built by iron. And oh yeah, I wanted to share this other, back to this is kind of a funny. I was like, why? I thought it'd be fun to show some O3 today, and O3 is the ChatGPT model. That is a reasoning model. And so you can ask it things like, how did iron change the Iron Age? Weapons, tools, and society. Could you quantify this? And so I asked ChatGPT and O3, to think for 3 minutes and 30 seconds, thinking about how much the Iron Age was changed by iron, and specifically in terms of weapons and tools and the rest of society. And so you can see here that for weapons, it we got, if you multiply the halved edge quality of early iron by a tenfold jump in numbers. So what they're saying is that back in the day, we could only produce bronze weapons and things like that. And so they were less strong, or they were stronger, but it was hard to mass produce them. And so but now you can mass produce stuff 10x more, but it's a little bit less strong. So roughly speaking, we 5x the amount of battlefield lethality, and so, and especially once steel spread, both quality and quantity were higher, locking in the advantage. So yeah, it let rulers swap prestige weapons for mass production. So instead of just having a few, like 100 warriors that all had good bronze stuff, you instead had 1,000 or 10,000 warriors that had iron and iron swords, and then eventually steel. So that's on the weapon side. And then on the tool side, yeah, it's similar. I mean, it was it extended the acreage. So it's these iron plows, 3x the amount of area that you could till. And then also, so that's the plow. And then it also allowed you to harvest better. And so they extended, they made more, allowed us to do more, and allowed it to be more efficient with the stuff that we were already doing. So it increased the amount of food that we had. So that's kind of, as they say at the bottom here, it swapped Bronze Age prestige goods for everyday commodities, multiplying swords on the battlefield by 5x and grain and granary by 20%. So that's an important thing. So iron was a crucial part of our history. It is, steel is crucial to our world today. And so where's iron? Iron's here. So yeah, iron, crucial to our history, crucial to our world today with all the steel production, and then crucial to our bodies in terms of ferredoxin, and also in terms of heme and hemoglobin. So yeah, iron, definitely S tier, which is great. Okay, so now we get to the rest of these. These are kind of funny: cobalt, nickel, copper, zinc. Honestly, these are all pretty similar to the titanium, chromium, manganese stuff. And so I'm going to put, cobalt is slightly different. It's probably still D tier, but I'm going to put nickel and zinc on the same level as titanium, chromium, manganese. They're essentially just things, zinc is a helpful anti-corrosion metal. And nickel does some strengthening, and these are essentially just steel making elements. The cobalt is interesting because cobalt is used as an electrolyte it's used as the cathode in lithium ion batteries. And so yeah, it's and so it's important. There's more cobalt mined in the world. There's this pretty interesting book that I actually haven't read, but have done some dives into how the Democratic Republic of Congo, 100 years ago, it was totally exploited during the Belgian times during King Leopold's reign, and that was bad and that was mostly for rubber production. And now it's used. I think 50% of the world's cobalt comes from the Congo and the Democratic Republic of Congo. And so there's a book about how the blood of the Congo powers our lives, how cobalt is needed for these lithium-ion batteries, and it's all being mined in the Congo. But cobalt, it's in these lithium-ion batteries, so it's kind of important, but it's hard for me to argue for it to be that much higher. I'm going to put it in, I'll leave it in D tier for now. It doesn't feel as important as some of these other ones. And then copper I think is probably got to be in A tier, just because copper is, copper is kind of cool. There's this what is it called? There's copper hemoglobin. I think it's called myoglobin. And it is hemocyanin, very cool thing, which is this is why the blood of octopus and stuff is like dark blue, is because instead of using hemoglobin in the like we use hemoglobin with this iron holding our blood for these creatures, for things like octopi, they use hemocyanin, and hemocyanin has a copper center. So you can see here it is where's a good picture of this? There's one of these things. Yeah, the copper structure of hemocyanin. You can see copper is at the center of it instead of iron. So that's kind of interesting. But yeah, the main reason why copper is important, in my opinion, is for electricity. And so you can see this book by Ed Conway, Material World, the 6 raw materials that shape modern civilization. We already talked about lithium. We talked about sand, and that is silicon oxide and silicon. We talked about salt, NaCl. We talked about iron. We talked about oil, and then copper. Copper is the last one. And so copper is, this is all of the lines for the internet. So these are the internet lines in the world. And so when you're trying to talk to people on the internet, you need to send electrons, and those electrons go over a copper line. And then similarly, these are if you're trying to just move electricity, not necessarily bits, but you're trying to move electrons to power things, here's all these high voltage power lines in the world. And so again, copper is the thing that moves electrons in the world, and therefore is super, super important. So I'm putting copper at A tier. So that's that. Actually zinc, I'm going to move zinc to B tier here, because zinc is, biologically speaking, I think it's more important than manganese or nickel. There's this thing called a zinc finger, and this is a little zinc metal ion that's kind of wrapped around this protein. And the zinc finger is a transcription factor, aka it does DNA regulation. And the crazy thing with zinc fingers is that if you look at, this is a random graph rather, of, let me see if I can find it. Those are homeodomains. Yeah, where are you? Where did you go? Oh, here we go. Beautiful. This thing shows how many. These are families of transcription factors. So we have, I think humans have 20,000 genes. I think we have like 2,000 transcription factors maybe. And of those transcription factors, those are things in our bodies that tell us when to run certain genetic programs, essentially. And so those transcription factors are they're made in different ways, but you can see here on the far left, this ZF1 that stands for zinc finger, and you can look at this. There's like 400 plus of the transcription factors are zinc finger or zinc finger adjacencies. And so versus these other ones, homeodomain, those are Hox genes, et cetera, These, there's P53, the guardian of the genome. And so most transcription factors have like 25 or less distinct motifs, but zinc fingers have 400 plus. So zinc fingers are very, very important. And because of that, I'm putting zinc as, it's important not only for corrosive metals and stuff, for corrosion resistant metals, but it's also important for biology. Okay, so what's up? It's welcome back to the full screen Reese. So we've gone 1 through 30 now, which is very cool. And now what we're going to do is we're going to look at the rest of the periodic table and we're going to say, wait a second, which of these are actually important? And so as you can see here, there's a lot of these things. And it's like, is europium important? I don't know. Is berkelium important? I don't know. What about bismuth, you know? And so essentially, my claim is that almost all these are F tier, aka not important, but some of them are actually important. And you can see, here's this image of 30 plus 14, where you can see, here's the elements that I think are important of 30 through 118. There's essentially these 14 elements, things like arsenic, things like lead, things like uranium that are important. So yeah, let's talk about each of these now. Starting with gallium. This is one, and in some of these I was like, what the hell is this thing? Because I didn't really know. I was preparing for this video. I was like, which of the elements 31 through 118 are important? And some I knew. I was like, I know that lead is important. It was important in the past, and it produces lots of deaths today. I know that uranium is important, but I didn't know something like gallium. So gallium is gallium's important because it produces this thing. There's this amazing Veritasium post on the blue LED, and the blue LED was hard to produce, but it's produced with gallium, and also indium. Indium is a little bit below here, and so you can see there's gallium, there's indium, and this is for various weird semiconductor reasons, but essentially it's hard to produce blue light, and it was only produced recently. We got this guy who did it, got the Nobel Prize for it, and it's because when if you're a semiconductor and if the electron is moving from one shell to the other, it sends off a bit of light when it does so, and sometimes that light is UV, like with something like silicon, but sometimes that light has a color, and so here's these different colors that you get from different. These are all different gadnium. How do you even say it? Gallium. All these different gallium. This is indium gallium. These are gallium phosphate or whatever. So these are different kinds of gallium, produce different wavelengths of light. And the blue wavelength of light was hard to produce for a long time. We had to make a very specific crystal structure to make it happen. And but once we did, check out this graph. This is again 03 doing some work, but you can see here's a beautiful image of the global share of artificial light by technology from 1900 to 2020. And you can see at the beginning, 1900, 10% of light was incandescent, 90% of light was other. So that's, whale wax and things like that. But then over the course of the 1900s, we got a lot of incandescent light, up to 1960, a lot of incandescent light. And then LED, you can see at the very end here, LED goes up a ton. And it only went up a ton at the end because before we could only produce red and green light. And that's kind of annoying but when you have red, green, and blue, you can then produce white LEDs. And so by the end here, we were able to produce white LED light, and that really, now we can produce a lot more light, a lot cheaper, because an LED is a light emitting diode. 70% of the energy that goes into it actually produces light, versus these old incandescent lights made by stuff like tungsten, which we'll talk about in a second. Those are, you just heat it up enough so that some of the heat turns into light. So it's kind of like a little fire or whatever. And so you're not spending that, only 3% of the energy goes into light versus 97% just goes into heat, versus a light emitting diode, 70% goes into light. So that's why frickin' our friend here, that's why gallium is so important. Gallium and indium are very important because they produce blue LEDs, which produce most of the light, most of the artificial light on Earth today. So yeah, I think gallium is, you could argue that it is gallium and indium. I think that they're both C tier. They're not, you could put them at B tier, but I don't think that makes that much sense. They're important. And Yeah, they're just important for light production today, but not obviously S, A, or B tier. They're also so that's what they do. The other, I guess, side note on indium is it. The other side note on indium is that indium is used to produce. It's very cool actually. Indium produces light. Indium produces. If you think about phone screens, indium is a material that is used, ITO, indium, maybe titanium oxide, indium something oxide, and indium is used to produce a screen that is transparent but still conductive. And so that's why on your phone you can click stuff. It's conductive, but it's transparent. And so that's very, very cool. And so that's the other thing that indium is used for is producing ITO, transparent but conductive devices. So yeah, so I think those are C tier, still important, but not crucial. And then we can talk about arsenic. Arsenic's important because it is, in the past, it was one of the main killers of, it was called the inheritance powder. And so 5 to 10% of all murders among royalty in, the 1500s, 1600s, 1700s were done by arsenic. Most poisonings back then were done by arsenic. And so it was pretty important for like power back in the day. I think that it is, and then these days it is also important. It's one of the worst toxins in the world, especially in like Bangladesh and stuff, where produces it's killed like, and you can see here's a map of Bangladesh and how much arsenic is still in the water there. It's way too much. It's in the wells. It's being taken out now slowly, but it is I think 5% of all deaths in Bangladesh in the last 25 years have been from arsenic poisoning, and so from arsenic related cancers. So yeah, it's not good. And so I think arsenic has just played an important role in history. Not that important, so I'm going to put it at D tier, but it is it's worth talking about, and I think it was worth being on the list. Okay, so that is arsenic. Now let's talk about, so we talked about gallium, arsenic, and indium. Now let's talk about silver. Silver and gold. Silver is important. Silver is mostly, it plays some role in electronics, but I'll mostly talk about it today in terms of its role as a precious metal. The copper and silver and gold, they're in the same column here, and they are all metals that are able to, they're not too rare, but they're not too, they're right in the middle where there's some of them, but not too much of them. There's more copper in the world. As you can see here, there's a lot of copper, there's some silver, and then there's some gold. And that's roughly based off of where they are in this chart, the heavier elements, there's less of them. I think that, and then they also can play a role where you can stamp them. It's easier to like put stamps. They're very, mutable, they're very ductile or whatever. So so there are these good things that make currencies, and silver, there's some silver in the world. There's roughly 10x more silver than there is gold, which is interesting. The price of silver is roughly 100x less than gold, kind of surprisingly, but it is an interesting, I'm pulling this up. So silver and gold were important. Silver was, I'd say, more important back in the day when it was the main, it was a key part of colonialism, and so you had, get out of here, gallium. So gold, if you think about, let me actually show this, here's, actually, maybe I don't have, that's too bad I don't have the O1 thing. Gold is let me just show my face then. Silver production back in the day was a key driver behind colonialism. The Spanish world, that was one of the main things they did, is they got all this all the silver from Bolivia and they brought it back to their world, their land. It made tons of inflation in the world. It 6x'd. The price inflation went. The price of everything went up 6x over the next 150 years. It made Spain. It gave them this bad thing where they were just buying too much but not investing it in their own production capacity, and so they fell behind the Protestant nations like the Netherlands or England or whatever. And so silver played a key role in colonialism, and then gold later obviously also played a key role, pulling the gold rush, pulling gold from Brazil, gold with stuff like the Gold Coast in Africa, gold with South Africa. Some of these gold mines are very interesting. There's one gold mine in South Africa that's 20% of all gold has been got from that one mine. And so gold is gold, there was the gold standard. So gold is very important. Some of these random maps and things with gold. Here's a cool gold mine, and then here's a map of gold production over time. And you can see here's the California gold rush that really put the U.S. on the map. And then you had South Africa. So South Africa was producing tons and tons of gold, a lot of which was exploited out of the country, some of which stayed in the country. But so that was South Africa. And then now these days, China overtook South Africa as the world's largest gold producing country. So this is, gold production over time. It kind of tells some stories about colonialism and stuff. And then these are Roman gold coins. So you can see that Rome was connected to India back in the day through trading, because we found gold coins in India. We found Roman gold coins in India. So I think something like gold and silver are important. I think that silver is less important than gold. It was important at the beginning of colonialism in the Spanish Empire. But let me find it. Where are you, silver? Silver, I think it's like C tier or D tier. I'll put it it's more important than arsenic. So I'll put it at C tier. And then gold, I'm going to put a little bit higher at B tier. Did, arguably A tier, and how much it has kind of changed. Honestly, it might be, I'll keep it in B tier. The gold standard is very important, and gold's role in the world and how, as coinage and as other things has been important, but I think I'll put in B tier. So so that is, that's silver and gold. And then something like tin. Tin is interesting because it was just part of the Bronze Age. Bronze is it's 90% copper and 10% tin, and so that's why tin was important. Essentially, you can see these things that have different. Most elements like carbon is C, nitrogen is N, oxygen is O, tin is SN, lead is PB, mercury is Hg, gold is Au. All of those elements were ones that have Latin names, and so that's why they have these old school names. And so you can tell, tin was probably more important back in the day because it has it was named before the periodic table, essentially. So it was named in the Latin way. But I think tin, I'm going to put tin as where are you? 1050? Yeah. I'm going to put you at D tiers as well. So tin, not bad. Ain't nothing wrong with tin. Now let's talk about iodine. Iodine and lead are kind of connected here. I think that iodine is important because iodine's weird. Iodine is you can see here, it's one of these organic elements. It gets in the same group, a reactive nonmetal, as carbon and nitrogen and oxygen, which is crazy. So iodine is the heaviest element that is used in our bodies and in biology in general, and iodine is crucial for cell growth. And so you can see this is thyroxine, which is the main thing that our thyroid uses, and this is essentially a hormone that goes in and stimulates cell growth. And so it's kind of like you pull on and off iodine, kind of like ATP to ADP, and it goes into cells and helps them do cell growth. And so iodine is it's an important molecule. It's one of the most important iodine is an important element and one of the most important molecules in our body, which is this thyroxine produced by our thyroid, one of the most important hormones that promotes cell growth. And if you don't have it, then you get you don't grow up to be big and smart or whatever. And so you can see, if you look at this is like a random, if you think about what's effective in education, some of the things that are effective in education are like curriculum and using some kind of digital technology or whatever. But the other thing that's important is iodine, universal salt iodization, the iodine global network. This is why in America, in the West in general, we have iodine in all of our salt, because iodine, you need the iodine for cell growth. And so I think iodine, and this was me asking a question, I was like, how much, let's scroll up to the top here. I was saying, if everyone had enough iodine and we took away lead and arsenic, what is the impact on global health? So these are just some of the most important things from a global health perspective. And you can see here that roughly speaking, this is in terms of, what is a DALY? Meaning? Quality adjusted life year, disability adjusted life year, that's what it is. So you can see that lead is super important. 35 million lives. Lead just messes up so many people. It's very, very bad for a lot of people. Iron, by the way, is another really bad one. Iron deficiencies are roughly as bad as lead. But iodine, if you don't have enough, if you have too much lead, that's really, really bad. But then iodine is one where if you have too much iodine, if you don't have enough iodine, then you don't get healthy kids. And so that's why everybody should have more iodine. And iodine is it's the heaviest molecule, the heaviest the heaviest element used in our bodies. And I think it's maybe, honestly, you could put it at D tier if you want it, but I think it's more important than arsenic or tin. And so I think it's I'm gonna put it at C tier. Yeah, iodine is cool. So that's iodine. And then lead is very connected. Lead is like the anti-iodine. Lead plays a role in our bodies where it is, this is just a random example of Lead Exposure Action Fund. These are people that are trying to make a world free of lead. Lead has been used in batteries. It's been used in all kinds of things. And it is, but as shown by that last 03 conversation, it is one of the worst contributors to death in the world. And this is because lead can pretend to be calcium in our calcium ion channels, the calcium potassium channels. And so it pretends to be it, and then it messes everything up. And so, yeah, lead is still producing lots of death in the world. And that's why I think it's very important. And so I would put lead at, honestly, it might be an A tier. In terms of importance, B tier or A tier, it's still it's really bad. There's still way too much lead in the world, and I don't like that. So that's lead. And yes, we've now done silver and gold. We've done arsenic and lead and iodine. We did tin. We did gallium and indium for those new age LEDs. Tungsten is important because it was the main filament for incandescent lights, and is still the main filament for incandescent lights. And so it was traditionally more important, and these days it's probably is not as important. But I think it's worth putting in. You could put it in C tier or D tier. I'll put it in D tier. It's in the future it'll be less important than gallium and indium, but in the past it was more important as a producer of light. So that is tungsten. And then mercury is similar to lead in that it's an old school element that was used more often. There's less deaths from mercury these days, but in the past it was used more often, for thermometers and things, and produced too much death in the world. And so I think it's D tier as well, because it is not that important these days, but was important. It has one of the Latin characters, and so that's that. The final couple here there's neodymium, and then there's these final three ones, uranium, etc. So neodymium is again another one where I was like, I was trying to understand all these elements, 31 through 118. I was like, what's important down here? And neodymium is important. Neodymium plays the role of it makes really strong magnets. And so you can see here in all electric vehicles, they have the rotor has these neodymium magnets in there. And so you use electricity on the outside, it produces an electric current, which produces a magnetic field. And then that magnetic field, the magnets on the inside are pulled or pushed by it. And so they spin the motor. And so these magnets it's an important part of China-US relations these days. And they just stopped, I think they stopped exporting neodymium to us. And it's similar to lithium ion batteries, and it will continue to play a pretty important role in our electric, any kind of electric motors will use these neodymium magnets. So I'm going to put it in C tier, I think, and important, but not as important as something like lithium. Yeah, so that is neodymium. And then the final ones here are thorium, uranium, plutonium. I'm going to put uranium at A tier, because the whole 19th century or the whole 20th century was in some ways a function of uranium. Both nuclear power is obviously incredibly important. 20% of all energy maybe is from nuclear power, 10 to 20%. And it is hopefully going to get more important. The Cold War was entirely defined by uranium, and it ended World War II, and with the two Hiroshima and Nagasaki. And it was kind of the culmination of a year's or a century's worth of particle physics and atomic physics. So uranium's important. It's the opposite of fusion. It's fission. It produces these chain reactions where you break, I think I have a random image here where you can see it. Yeah, you get unstable elements that break into smaller elements, producing more neutrons, which then go on to future ones, and then also producing some energy, because you lose energy through E equals mc squared, you lose mass in the reaction, and then that reaction turns into energy through E equals mc squared. And yes, it produces energy and it produces bombs, and has kind of totally defined the 20th century. So I think it is. So uranium, I'm gonna put it at A tier. I think plutonium, I'm gonna put it at D tier probably, because both plutonium and thorium, plutonium is important because it is the ignition, the pit of these uranium bombs are made of plutonium, so that's important. Plutonium is sometimes used in deep space expeditions and stuff like that as a fuel, but it's less important than uranium. Thorium is some of these new reactors that are coming into play are these new thorium-based reactors. So it's kind of a different way to make nuclear reactors using thorium as part of the fuel. So yeah, I think thorium is worth being. It's not that important now, but will continue to be more important over time. Okie dokie. So with that, oh my God, we did it, people. We freaking tier listed. We did the whole tier list. Let's get a good list. Let's get a good look at our tier list, and just make any last notes or last changes. So the first note, these first S tier elements are. Well, the weird thing about atoms is that, or about the elements of the periodic table, is that the only difference between all these things is just the amount of protons they have. This one has 1 proton, this one has 2 protons, and this one has 3. The amount of protons, then you get the same amount of electrons going around the outside, and then you also get a certain amount of neutrons. At the beginning, the same amount of neutrons as protons, and then over time, you get it to balance out, you get like more, so if iron usually has like 30 neutrons or whatever. But yeah, so it's just weird because they have all these different names and they do all these different things, but atomically, they could just be called 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if you were just to look at them as atoms, you wouldn't think that it was that different. 1 paperclip's not that different than 2, not that different than 3, etc. But because of how chemistry works and because of how electrons work and covalent bonds and ionic bonds, they operate in these totally different ways. So it's a very cool, very kind of strange, cool thing. Yeah, these S tier elements, hydrogen and carbon, hydrogen S+, carbon for everything, making all the chains, making all the structures in life so amazing. Silicon, the sand of Earth, and also the future substrate for intelligence. And then iron, the structure, the most important metal for biology and the most important metal for steel for society. So it's those four are amazing. These next range is amazing. Helium's kind of a weird one out, but 24% of all atomic mass in the universe is helium, so it's got to be there. And then you have obviously these amazing elements of nitrogen, oxygen, phosphorus. Those are just classic organic elements that are in everything. Sodium is it plays a role in biology. It plays a role in human history as an important thing. Calcium plays a role as cement and also in biological shells and mollusks and stuff. Very important. Copper is the wiring behind civilization, so very important. And then uranium totally changed the 20th century. B tier, lithium is in these batteries, which is amazing. And it's actually A tier as a side note. Yeah, it's just interesting which ones are. Helium's important universe-wise. Nitrogen, oxygen, phosphorus are important biologically, and then copper and uranium are important for humanity. So that's kind of interesting. B tier. Lithium-ion batteries. Magnesium. I wish I understood it more. Chlorine has saved tons and tons of lives. Chlorination. Aluminum is a really just a good metal. Nothing wrong with a good metal. Zinc is similar to all the other transition metals, but also it has zinc fingers. Gold it's just this weird off chance, weirdly important thing that's been currency and has totally changed geopolitics and political economies. And then lead is still a huge killer, and I hate that it still kills so many people in the world. C tier, but it's important. It's B tier level important. C tier, some of the final organic elements, sulfur, potassium, whatever, and then all just the classic, titanium, chromium, manganese, nickel, things that make stainless steels corrosion resistant. Gallium and indium producing tons of light in our world through blue LEDs. Silver, really important geopolitically. Iodine, really important for our health. Neodymium, really important for these future magnets, for future electric vehicle motors. So yeah, C tier is just full of just good, steady elements. And then D tier, fluorine. No one cares about fluorine. D tier elements are ones that just barely made it into the list. They're not all these random ones down here, but they are not. They're not important. Fluorine. It's just like it's like an intense chlorine. And so it just it's too crazy. Cobalt is interesting, and it geopolitically these days is moderately important, but it was a hard pitch to make it higher. Arsenic's been more important, killed a lot of people, still kills a lot of people, but hopefully not that many people. So D tier. Tin again was important. Tungsten was important. Mercury was kind of important, but not that important. Honestly, Mercury could totally be F tier. Thorium and plutonium are kind of helpers for uranium. They're essentially all these 22, 24, 25, 28, titanium, chromium, etc. Those are like the stainless steel makers with iron, and then thorium and plutonium are kind of similar ones, but for uranium. So that's why they live there. And then these final ones, beryllium, boron, neon, argon, scandium, vanadium are the part of this periodic table up here where it's like, yeah, we don't really we don't care about you. You could just be removed from the period. They're not really worth thinking about, and you should concentrate your time more on these other ones. So yeah, that's the periodic table. I hope you enjoyed it. I'm curious what you think. What is your favorite element? What did I get wrong? What did I get right? And thank you for listening today. I have no idea how long this video is. Probably crazy long. And it was fun to make a tier list. And let me know what other tier lists you want to see going forward. And thanks to my patrons on Patreon and the supporters of Root for supporting this educational content. Thanks.